Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to kind of demonstrate how free bodies and Newton's laws are applied for problems that are problems about circular motion. So in this example, we've got this automobile here that's driving around this circular path that has a 50-meter radius. And in this example, this path is going to be a nice level road, and what we're going to try to calculate here is we're going to try to find the maximum speed that this car can safely go around in the circle. So I've drawn a few snapshots in time. I'm going to take a moment here and draw some velocity vectors. So at this instant in time, the car's velocity vector might be something like this. And then at another instant in time, the velocity vector might be something like this. Now in this example, this is going to be a constant speed example. Okay, so at another instant in time, the velocity vector might look something like this. And again, I'm trying to draw these vectors roughly the same length here because I'm imagining a constant speed example. So what are this v is here, it's the same here, it's the same here. Now, again, I'm going to talk about what's the same, what's not the same. The v, the speed, is the same, but the velocity vector of the car is changing in direction. So this car is constantly accelerating. Right? Now, when we're analyzing problems in physics, most problems break down into a couple of types. There's Newton's second law type of problems and work energy type of problems. In this example, this car is not going up or down a hill, its speed's not changing, there's no changes in kinetic energy, there's no changes in potential energy. So any work energy equation we write for this car is going, the potential energies will be constant, the kinetic energies will be constant. It will simplify down to just 0 equals 0, which is true, but it's not particularly useful. So this problem is going to be handled by using Newton's second law. And if we're going to use Newton's second law, we need a free body diagram. So now I'm going to draw a free body of this car at that position. The first thing I'm going to use is kind of a snapshot of the car. What does it look like if I'm looking from this viewpoint here? So this is kind of representing an eyeball. So the car's coming right at me. I've already drawn a picture over here to represent the car. Now in that picture, I'm going to start drawing force vectors. So gravitational force is typically an important force on most systems. So force vectors, draw that force vector down, give it a name, mg. Okay. There are 4 tires in contact here. Now generally what we do is lump those together. There's 4 normal forces. I'm going to kind of just lump those together, call that one normal force up. And then the force that's keeping the car on the road is a frictional force, right? Imagine, that I could snap my fingers or actually imagine that this car comes around this path and hits this nice icy area here. And you ask yourself, where is that car going to end up? The car's going to end up down here somewhere. Because if this is ice in this region, this car's not going to be able to change its velocity vector. It'll just go right off the road and end up here. So the frictional force between the car's tires and the road is what allows it to change the direction of its velocity vector. So basically the frictional force is what's keeping this car on its circular path. In this free body, the frictional force is applied at the tires, and the frictional force is pointing inward. So the frictional force in my picture is going to go this way. So there's the free body diagram of the car. Now, whenever you're dealing with free body diagrams, it's very important to get all the forces in their correct directions. So we got a normal up, mg down, frictional force to the right. If we ignore air drag, there's no other forces to worry about in this problem. Now the other thing we have to realize is the acceleration direction. This car is not accelerating up or down. If it did, it would come right off the road. So the acceleration direction is to the right. I'm going to go ahead and put an arrow here. And that acceleration is a centripetal acceleration. So it has a magnitude of v squared over r. So there's 2 equations we can write for this free body. Equation number 1. Sum of all forces in the y direction equals 0 because the car's not accelerating up or down. I'm going to go ahead and denote which way I'm calling positive. So we look at our free body, that's going to be the normal minus mg, and that's it. In this problem, the frictional force does not have a vertical component or a y component. So this sum is equal to 0. So from this equation, we can get that the normal is equal to mg. In lots of problems, the normal is equal to mg. Lots of problems, it's not. You know, things that could change that. If this track were banked in some way, shape, or form, that would change the normal force. Right? Second equation we can write. Go ahead and put this right here. Sum of all forces in the x direction equals ma. That's Newton's second law. I'm going to go ahead and do right positive. Remember Captain Rod's rule of thumb. Identify the acceleration direction, call that positive. And that acceleration direction is to the right because if we look at this picture, this car is undergoing circular motion. When you're undergoing circular motion, there's always a centripetal acceleration towards the center of curvature, which is here. So look at my viewpoint of the car. We're looking like head on. Center of curvature is here. That's why the acceleration vector points to the right. When we write this equation now, we look at our free body. There's only one force in the x direction, the frictional force. And that has to equal m times a, the acceleration. And because this is a centripetal acceleration problem, or I mean because it's circular motion, that acceleration can be written mv squared over r. And I notice I put little r here. I meant that kind of in general, but in this problem, the radius of curvature is what I call big R here, 50 meters. So I'm going to go ahead and put a capital R there. Okay. So we've got these two equations from Newton's second law. Normal equals mg, and the frictional force equals mv squared over r. So the frictional force in this problem is the force that would be called a centripetal force. It's not even important that you recognize that to work the problem. What is important is that you recognize there is a frictional force and get it in its correct direction. Okay. Now, these two, the normal and the frictional force, are linked by the coefficient of friction. The maximum possible frictional force is equal to the coefficient of static friction times the normal. And I'm going to use the static coefficient of friction because I'm looking for the maximum speed. So putting these two equations together, we're going to have the coefficient of static friction times the normal equals mv squared over r. Right? The normal force is equal to mg, so this is going to be the coefficient of static friction times mg equals mv squared over r. And I'll notice now that the masses go away. Right? This problem is not dependent on the mass of the car. So I'm going to go ahead and put that r on the other side. So we're going to have v squared equals the coefficient of static friction times g times r. Right? Now, million-dollar question is, what do we do about that? Well, if we had a static coefficient given, we would use that. We're just going to assume really good tires here. Coefficients of friction typically range between 0 and 1. And if you go ahead and look up the static coefficient of friction between rubber tires and concrete, it's right around 1. So I'm going to assume best case scenario here. So we're going to have v squared equals 1 times 9.8 meter over second squared times the radius of curvature here, which is 50 meters. And I can go ahead now and get a v out of that if you give me a moment. I get about 22 meters per second out of that. I'm going to go ahead and convert that to mile per hour just to see what that comes out to. So 22 meters per second. To convert to mile per hour, the first conversion factor would have to have miles on the bottom, meters up top, and there's 1,609 meters in 1 mile. So the way I have this now, we would be in, let's see, we're meter per, whoops, I think I got that upside down. Let's see, this was 22 meter per second. I have this upside down. Let me go back and change that. When you're dealing with meters and miles, you got to make sure and distinguish them in a different way. So I'm going to go ahead and put meter here. Then our conversion factor, we're going to want to have miles in the bottom, meters up top. I'm sorry, I did it again. meters in the bottom so that they cancel. Miles up top, and there's 1,609 meters in 1 mile. And now I want to convert this to hours. So my next conversion factor has to have seconds up top, hours on the bottom. There's 3,600 seconds in 1 hour. If I go through and calculate this, let's see, we're going to have 22 times 3,600 divided by 1,609. And I get about 49 mile per hour, approximately 49 mile per hour. And again, checking the units, my meters cancel, my seconds cancel, we're left with mile over hour. This wasn't really a requirement of the problem. I was just looking for Vmax. The important things for calculating Vmax: drawing the free body. Now, I could have drawn the free body maybe at this position. If I did so, looking from behind, what would the difference be? Well, the car would be going away. The normal would still be up, the mg still down, but the frictional force would be towards the center of curvature, which is here. So the frictional force would be to the left. The acceleration vector towards the center of curvature, also to the left. But these equations would be identical. You'd still end up with n minus mg equals 0, and the frictional force equals mv squared over r. You'd still end up with 22 meter per second and 49 mile per hour. So again, the point here was how to apply Newton's second law to a problem involving simple circular motion. I think that hopefully it does that, and I'm going to call that a day. Everybody have a good afternoon, or morning as the case may be.